Okay, so I got a problem. Balls end up all over my floor. I don't know why, but with young kids at home, I've kind of learned to stop asking questions after a little while. But what I do know is that I'm not going to be picking these things up off the floor myself. And given that I've been teaching robotics for over a decade now, I figured that I would build a robot to be able to do that for me. This thing can drive around in any direction it wants thanks to its omnidirectional drive. It's got a pivoting arm and then an extendable arm as well so that it can reach out to a little bit over a meter as well. And today I'm going to break it down how this whole thing works for you and how that telescopic lifting elevator makes this whole thing really possible. And if you've been following along with the First Tech Challenge for the BIOBUZZ season, there's a chance that you might have to build something similar to this, which is picking up a ball about this size and then picking it up to another level. So this might be an interesting way of solving a potential challenge for you too. So this is the main robot at a glance. It's got something called a holonomic drive or an omnidirectional drive, and that these are wheels called mechanism wheels. And effectively what it allows you to do is allows you to spin the wheels forward, and that moves the robot forward and backwards. But because it's got these little 45-degree angled rollers on it, if you spin one wheel inwards and one wheel outwards, you'll actually cancel out your direction and you'll actually end up moving on strafing directions. So you can actually pivot sideways as well as rotate, which is pretty slick. So having 4 different mechanism drive wheels means that we're capable of rotating ourselves around, strafing, and having sort of an omnidirectional movement in any sort of way that we want. But the thing that really makes this thing magical at picking up some of these little yellow balls is this little piece of kit here. This is a telescopic elevator or a telescopic lift. And what makes this thing a little bit like magic is that it has one large box that's 40 mil by 40 mil, then another second box inside that's 20 mil by 20 mil, and then another third box inside that is 20 mil by 20 mil. So it's kind of like those Russian dolls you used to play with as a kid, and then they all kind of telescope and lift inside each other. You've probably seen these before on a tripod when you extend that out, or a selfie stick or something like that. Now this telescopic elevators from a company called Offset Robotics. In the past, I've taken a look at their slide that was string driven. I was quite impressed with the kit, but now they come with a new kit that is belt driven, and it solves a lot of my gripes that I had with the string driven kit. Now, full disclosure, Offset Robotics were kind enough to be able to send this upgraded belt kit over to me, but as always, my thoughts and opinions are my own. And the cool thing about this box elevator is that this thing is super rigid. Another common way that robots sometimes lift things up and out of the way is with a set of linear slides here. Now, linear slides are kind of like drawer slides. These are really common inside of drawers, obviously, or inside of a kitchen or a bathroom, your dresser, whatever have you. And the cool thing about these is that they can extend out and reach out, and then these little wheels slide in and out. But the problem with these is they're not particularly rigid when you start to get really long lengths. So when I extend out almost a meter, these things will flex quite a bit. And despite them being a fantastic method for extending things out, it does mean I take up a little bit more space. And when it comes to pivoting, there's a bit more mass that I need to apply on this when it comes to a pivot. If this were just in a fixed plane, I really like using these linear slides. But the problem with my design is that I needed to come up with a way of being able to tilt this whole arm up and down. And the nice thing is this telescopic elevator makes it so that this thing is rigid all the way across. If I were to extend this thing all the way out and have any flex here, I end up actually with very little flex on this whole subsystem, even when I'm almost a full, more than a meter out from the original position of it too, which is really, really slick. And the way that this thing is able to get itself in and have so much of that rigidity is with these little ball bearings on these slides here. So this box tube here rests on these 2 ball bearings, and on the opposite underneath side, there's also an additional 2 ball bearings that constrain the system on this orientation. Then on the other sides, we have another set of ball bearings here and another 2 on the back side that then constrain it in this direction. So that is what's constraining the outside of this box tube in and out. On top of that, on the back of this slide, and let's change the view angle here. But on the inside of our box tube here, we also have an additional 1, 2, 3, 4, 5, 6, 7, 8, 2 more sliding that are now pushing on the inside of the box tube that it's nested in. So not only is this box tube being supported on the far end by those 8 ball bearings, it's also being internally constrained here by those other 8 ball bearings. And that makes it quite a slick little piece of kit. Now, in the past, I've also used other box tube lifts. This one is a string-driven box tube lift, and I'm not a huge fan of using strings in my robotics projects, mostly because strings are really finicky to be able to drive. They're really finicky to be able to get tension correctly and so on. And when a string snaps, it can be a real nightmare to get things back together, which is why I'm a huge fan of belt-driven systems. It makes these things a lot more robust. It makes it a lot faster to get it up and running. Now, when it comes to actually powering and how this thing is able to actually drive itself up and out, you can see we've got one motor here that spins through these motors, or spins through these gears, sorry. And then on this gear, it's got a shared shaft here, which goes through a motor pulley. Now, this motor pulley, as it rotates and as it pulls backwards, it actually starts to pull on this belt. And this belt is run up and tied to the bottom of this slide here. And as you pull on that belt here, you're actually, and we can see here as the belt starts to retract, as this belt starts to move backwards, because it's constrained down in this bottom, it has no choice but to then lift itself up until we get to our eventual endpoint where it can't go any further. The same is true of this top section of our slide. And this is rigged. Typically, when we rig things, we rig them in something that's called continuous stringing. So you will lift one channel, will come all the way out, and then the second channel will come all the way out. But this box tube slide means that both of these independent or inner sections move together at the same time, and they move in and out at the same rate, which is also a really slick little piece of kit. Now, one of the questions you might be wondering is, how do you know when this telescopic lift is at its bottom and at its top? One of the ways you can do that is with a motor encoder. In the back of these motors, there's a little spinning magnetic dial that knows when it's rotating. So as we see that motor rotates up, it's spinning and adding clicks in one direction and then adding clicks in another direction, so we know what our start and end points are. Another way is you can use something called a magnetic limit switch. And down here, I've got a little magnetic limit switch. On the end of my tube elevator, I have a little piece of aluminum extrusion from Misumi. And then I have a magnet that runs over something that's called a Hall effect sensor here. And when this magnet comes near this Hall effect sensor, it lights up blue and it says, hey, I've got something near me. And at this point, my slide is also fully retracted, so I know that I've now reached the bottom of my line. One of the benefits about robots is you can always add lots and lots of sensors. So I've got motor encoders on this, as well as a Hall effect sensor, so I know when I've brought myself down. Now, when it comes time to actually pick up some of these balls, we use things called compliant wheels. In this case, I'm using a compliant star or a boot kicker to be able to pick these things. So as this rotates, these little stars are a little bit wiggly and allows me to get a little bit of extra compliance on these balls that then allows me to pick these things up. And it just kind of rests as they're spinning on this little L-shaped kind of ledge that I've built up for it. And as this thing spins, it forces those balls back in, and I can get about 7 or 8 balls in one solid go off of this as well. This thing is driven by a little motor up here that's then driven by a chain to be able to pull all of the balls back inside the robot. Now, the last piece of the robot that actually makes this whole thing kind of pivot and rotate up and down is this very large gear system. I've taken a 6,000 RPM motor. I've ran it down through a 1 to 64 reduction. I've reduced it through 3 planetary gearboxes to a 1 to 64 reduction. So every 64 turns ends up with 1 rotation in the back gear. And then I have further reduced that even more with a 5 to 1 gear ratio here. So for every single 5 rotations from that output shaft, I end up with 1 rotation of the arm. So I've actually got a 320 to 1 ratio here. So for every time that this motor rotates 320 times, this will rotate a single rotation all the way around. And I have this on a constrained axle that goes all the way through. And you can see that as this large arm pivots up, that large motor is able to spin, and we can get quite a bit of rotation up and out of that arm. Now, 2 ways that I know to keep track of where this arm is. Similarly, I've got another motor encoder on this arm, but in this case, I've actually put a motor encoder on the output shaft. So this, as this little wheel spins around, it keeps track of how far the actual arm itself is spinning. Because if I had a motor encoder just on the motor itself, as that thing spins, I wouldn't actually know what angle this arm is now at. But because I have a motor encoder that keeps track of that main arm, now I know how far this thing's able to rotate. The last little safety feature I have, this is up at the front here, I have another Hall effect sensor. That's got a magnet on the end of my pivoting arm. You can see it right there. And then there's a second Hall effect sensor down below. Now, I really am a fan of this Hall effect sensor. It's a new product out from AndyMark, and the reason I quite like it is that it has a rather far distance trigger for me to go. So I found that I can get almost 1.5 centimeters, almost 2 centimeters away, and this thing is still triggering reliably when a magnet comes up in contact with it. So it means that I don't have to have my magnet really directly beside this Hall effect sensor, whether it's on the left, the right, or top of it. I know when this arm comes down that my arm has now reached itself to rest, and it's now resting on the bottom of my robot as well. So overall, I'm pretty happy with how this robot has ended up performing to be able to allow me to not have to go and pick up any other balls in the future. What I'm probably going to do in the future is be able to make this thing move autonomously, in which case I'm going to add on some camera vision so that it can now know where a ball is in front of it and then automatically drive towards that ball to pick it up on its own instead of me needing to manually drive that thing around. If you want to know how to build one of these for yourself, I got the full CAD for this robot available on my website down below that you can join out the community and get access to all my other CAD files and code snippets, things like that in the future. If you want to know how to program one of these, I'm going to have some tutorials on how to program the arm, how to program the extension lift as well, so that you can do this on your own robot too. And of course, if you want to check out the box tube elevator for yourself, I'll have a link in the description down below. It'll give you a 5% discount off on that. It also helps me be able to make more videos and tutorials like this for you in the future. And one thing, keep in mind, if you do want to pick up one of these tube elevators for yourself, I'm personally a big fan of this. I really like that it's a belt-driven kit. A few things I'm not a big fan of, though. I would definitely swap out your axles. The axles here, I would say, were not the best tolerance designed in that I actually couldn't get any sort of hubs on these. It's supposed to be 7 millimeters, but this was actually more like 7.3, 7.4. So quite a poor tolerance there on that one. And then I would also suggest that you swap your own belts, because the belts that came supplied with the Offset kit were stretched so badly that I'm actually breaking my steel cord inside. So I had to swap out for some higher quality belts in there as well. But provided you make those couple changes, overall, I'm a pretty good fan of this kit, and it really is the only thing on the market right now that allows you to get a telescopic lift in such a small form factor that despite some of its shortcomings, overall, it's a pretty solid piece of kit. Hope you had a good time exploring through a ball picking up robot with me as we go. And as always, best of luck on your next robotics project.